Welcome everyone to Mark Voids a Warranty, sponsored by Royal Circuit Solutions. Well folks, I've got good news and I've got bad news today. The good news is we're taking something apart. We're voiding a warranty. The bad news is my viewership has been down. So, to keep Mark Voids a Warranty going, I've promised to double the number of viewers that I'm getting today. That's right, double. So, if we can get to 2 viewers, I'll have reached my goal, right? That'll be fun. Anyways, today we are taking apart a HP laptop. Now, this one really has offended me. Its performance has just absolutely gone to crap. It can take, 10 minutes to turn on. You can't really do anything with it anymore. So HP, you have things to be ashamed of. This isn't a software issue, it's a hardware. You can't get anything going on this. Something's wrong with the board or the chips on it. I'm not sure, but either way, it's no bueno. So, anyways, let's get going. So this is the HP laptop. It's a 14-inch. It's got a screen, little webcam in it, keyboard. Backside, we've got some ventilation, not much. One of the nice things, it has the USB-C, HDMI, but it still had regular USB, which comes in handy. And a full-size SD card reader. So we've got to figure out how to get into this thing. And it's either going to be under the feet or it's going to be under the keyboard. And it looks like it's going to be under the keyboard. Oh, there's a screw. I'm just taking off all the little rubber feet right now. So we do have 2 screws on the back side, so those will certainly need to get popped out of there. If I can find the right screwdriver. Selection. Hey Josh, we're at 2! You and Brian! Woohoo! We made it! You see, there's been talk about canceling Mark Voids a Warranty. That's right, I'm being oppressed. The man is trying to oppress me. But you know what I always say? Don't let the man get you down. I mean, if there's anything I say, that's what I say. Oh, why is that screw not going anywhere? I'm spinning, it ain't doing anything. All right. Well, let's take a look underneath the keyboard next and see what we can find. They do sell special tools for key removal, and I happen to have one. This is by Craftsman. It's 1.25 inches. And you really do kind of want to be careful with how you do this. But really what I'm doing is I'm looking for screws underneath. And I think we're going to find one. Definitely want some eye protection for this. And remember, don't hit it too hard with the sledge. You want to be able to put these back together at some point in the future. Oh, that was a loud one. Seems like we probably should have gotten a bag to collect these. Huh. Well, I haven't really found any screws yet. Maybe this thing just snaps apart. Yeah, nothing's looking like a screw. But, I tell you, that was fun. Let's keep looking. It is possible that this thing is designed to simply split open. I'm not sure. Oh, there was a split. Ah, there we go. See, computers are made either out of aluminum or plastic. The aluminum ones are a lot more dependable. I'm running into issues with that screw again. It still just is spinning. It doesn't want to come out. Huh. Well, we'll get there. Oh. And guess what else I found? I didn't even see those before. There's 2 little screws. They're just hiding right there. They're little baby ones. I'm going to need a little baby screwdriver. Yep, we are pulling out all the stops today, Josh. We are having a good time here. But remember, even though we're having fun, you never want to do anything that you can't put back together. And I could fix that. You know, a little super glue and ramen. I mean, you just blend it right in. You'd never even notice. Oh, man. Do I have anything that's going to fit that screw? This is a low profile screw and there's not a whole lot to bite into. There we go. There's one. Come on. Come on, little guy. There we go. Yeah, if anybody knows why computers just stop working after a while, please leave a comment. There it is. Now we don't have to worry about that screw anymore. But we have our first look at the inside of the machine. Oh, welcome, Jason. We're at 3. Woohoo! So we've got our first look at the board. You know, so already can identify some things. You know, you can see some little coaxial cables. So that's going to be our Wi-Fi chip. You know, we've got a lot of FFC connectors. We've got a hard drive in there. Those are always fun to take apart. What looks like replaceable DIMM memory. Those are always fun to look at. So we'll take a look at that. And then a giant heat pipe. These things are magical. I love heat pipes. So anyhow, let's get into it and start popping screws. And if we have any trouble doing this, what we're going to do is flip it over and go right back. We're going to get some more keys off. You never know when there's a screw hiding under a key. Better to be safe than sorry. Brian, you said power supply. Frank says, yes, Alex. Frank says less screwdriver, more hammer. I tell you, I'm willing to use the quick disassembly on everything except for battery packs. I always worry about a uncontrollable fire here in the office. We'll have to take one apart outside one day. All right, so let's see how hard it is to remove a HP battery. Oh, man, that just pops right out. There's nothing to it. Interesting, interesting. So that's nice. Although we didn't really have any issues with the battery. The issue was with performance. Just processor would run all the time. I mean, it was just awful. Okay, so now we've got connectors to the other side. So that's going to be our touchpad and our keyboard. This one appears to be the hard drive connector. So we'll pop that. Probably should start collecting these screws. You never know when they come in handy. I mean, overall, as far as repairability goes, this isn't all that bad. I mean, I could get to everything relatively easily, right? Batteries out, hard drives out if I wanted to replace that. I haven't actually seen this technique before, where they've taken the hard drive and moved it to a FFC cable. I mean, nice low profile. I like that. That's slick. A giant multi-pin connector for something. I don't know what that is yet. But we're just going to keep taking out screws and see what we see. This board I'm taking out now, and actually, I can probably give you guys a bit of a closer look. So over here, this is the SD card reader that's coming out. And it's held in place with at least one screw. I'm sure there's more. I just haven't found them yet. There it is. Nope, just one. So our SD card reader, it's got a little motherboard, a chip right on it, and then we go to an FFC off to the main board. So after we do a little more teardown, we'll take a closer look at that. FFC cables all over the place here, connecting all sorts of stuff. So now we're just going to move around and start popping screws at the edges that hold things in. This is a little tiny board over on the side that I forget, does this do the HDMI? No, this is 2 USBs, audio, and a USB-C. So we've got a little piece of plastic here. I don't know what that does, but I know how to remove it. Pops right out. Speaker. That's a speaker cavity. I'll be darned. So you've got a speaker here, and it's in a sealed cavity, presumably so it can build up more acoustic energy and be louder. So that's kind of neat. All right, we're going to keep popping screws. I can go to a wider view if you guys like. Wrong button. There we go. Boy, I tell you, we're having all sorts of fun. Once I get all of these boards out, we're going to take a look at them and see if we can learn anything from them, either about their designs or how to maybe improve our designs or save money. Every connector, every FFC is an expense. So you have to be careful using that. It's a combination of figuring out best bang for your buck, right? So if you can modularize your laptops, you know, so let's say that, you know, you've got a whole line of laptops and this board goes in every one. Okay, put a connector on it. Or if you can do this board in 2 layers and the rest of the laptop is, you know, 12, and, you know, you can save a little bit of panel real estate. Okay, do it. But other than that, I mean, you have to be careful how many connectors you have. Every connector is a point of failure. Every connector is an expense. All right, so we've got a high flow fan that is connected right there. That's kind of interesting. So these things are centrifugal fans. They pull air in from both the top and the bottom, and then they spin around real fast and shoot it out sideways. So neat little guys. And it's blowing through the heat pipe. Heat pipes are also incredibly interesting. So with a heat pipe, it's actually a semi-hollow tube. There's space in there, and in there is sintered copper. So you take it and you put a chemical in there with a relatively, you know, well, you can choose your boiling point. You can do whatever you want. So over on this side of the board, it heats up that liquid and it vaporizes it. And then when it's in the vapor form, it travels along the heat pipe over to here, where the fan blows air on it and cools it down. Well, it cools down, it becomes a solid again. Comes back over here. It all happens without any moving parts, right? The liquid's moving, but there's no pumps to fail. I mean, it's ingenious. Now, regular copper has a heat capacity of something, I forget exactly what, it's like 400 watts per meter Kelvin. It might be 30 more or less. I don't really remember off the top of my head. Silver, barely a little bit bigger. Heat pipes, orders of magnitude better. So if this was just a copper pipe without that liquid in it, 400 watts per meter Kelvin. With that liquid in it, I mean, you're talking not like 4,000, but more like 40,000 watts per meter Kelvin. I mean, they really move an absolute ton of energy. You can pick up heat pipes on YouTube, on eBay for, you know, like 10, 20 bucks. Play with one, grab one, you know, put one into coffee and touch the other. You know, use the heat from your hand to just absolutely melt through an ice cube like a hot knife through butter. They're fun. I never get rid of those. All right. Look at that nonsense. By the way, before I go any further, look at the nonsense they got going on over here. This is how they covered their processor in thermal paste. It's spotty as all heck. Let me just show you the parts that they were supposed to aim for and that should have had full coverage. They're these shiny ones here. That's what they were trying to get. Man. Heat paste is an art, people. I'm telling you, HP, if you overheated your own processor because you didn't put the heat paste on right, I'm going to be disappointed. The internet's going to be disappointed. And look, I have 5 concurrent viewers right now, HP. I'm an influencer. Yeah, you better watch your step. That's all I'm saying. Okay, so I'm just going around and we're trying to remove the logic board right now. Once we get all the boards out, we're going to take a look and see what's going on. So I still have a connection up here to something. Might be the LCD backlighting. So that's the logic board. We'll take a look at that in a minute. So now we've got everything clear. On the other side of this is our keyboard. I'm going to keep unscrewing things. These are the friction mounts for the LCD, so we can get into that in a minute. This is the area where we had that screw that just wouldn't come out. I mean, it just spun and spun and spun. All right, folks. So how are we doing out there in comment land? Anything you guys want to see or want to know as I go through this? Or are you just eating your lunch and kind of have this on in the background? I think that's what I would do. I'll also tell you, we're having these Mark Voids and warranties edited down. There's another speaker into shorter segments. So we'll put those up on another playlist. So if you want to see the highlights and you don't want to sit through the hours long, which I understand, that'd be cool. Okay, so here is our power connector. And it looks like they couldn't get enough current through single wires, so they doubled up everything. Totally cool. It's always something good to know. All right. We are free, but we have not yet gotten the touchpad out, and we are taking this thing down as far as possible. Piece of metal there. Get that off. Also, we're doing okay on viewership, but we're not where we want to be. I'd like to get to 500. That was my goal for last year. We're not quite there yet. We're 23 shy. So if you haven't already, make sure you like and subscribe. Tell your friends, tell your neighbors, tell your friends' neighbors, and your neighbors' friends. But if you have subscribed, don't subscribe again, because that's actually unsubscribing you. That's something we don't want. See, viewers equals clout. We want clout. I want YouTube street cred. I have no idea why. And I don't know what I'll do with it, but I guarantee you that tiny little bit of power will certainly go to my head. Oh, one more screw. There's all sorts of screws. These are tiny little metric, and I don't know how small. They're like M1.4s and whatnot with large heads. Okay, we've gotten almost everything off, but I'm still curious what's holding that keyboard in. I bet you there's some hidden screws we haven't found. Nope, I was wrong. Oh well, live and learn. But I do wonder what's holding that thing in. I don't know. Oh, is it glue or is it melted? It's melted in. Hate when they do that. So what they do is they put this thing down, and there's some little bosses that stick out over on this stuff. And what they do is they just hit those with a little soldering iron and melt those, and they melt them into place. Not much you can do repairability-wise when people do that. Let me see if I can view in or zoom in here for you. Wrong one again. So you've got all these little melted spots that are holding it in. Don't you hate that? I know I hate that. But who knows? Maybe we can use this keyboard in another project. Let's go ahead and pull it out. All right. That's in good shape. I think we've got this thing apart. What do you say we start looking at boards? Oh, yeah. No. All right. So here is our first board. This is the main motherboard for the PC. I really don't remember. Oh, yeah, this was the RAM connection down here. We've got some type of IC. We'll look at that under the microscope in a minute. This appears to be the main processor. We've got some missing components. They kind of have the patterns that make me think they're memory. So I don't know what that's about, but maybe we had a video card add-on and extra memory that go on those LGAs and BGA arrays. Connections down to the keyboard and the touchpad. Over here we've got our Wi-Fi. I don't remember unplugging those RFs. And then off-board connectors to USB, HDMI connector, and whatnot. All right, let's get into this bad boy. Or I guess I could do this view first. So HDMI, USB connectors, off-board connectors. This is the spot where the Wi-Fi module plugs in. Power. I don't remember. I think that was our keyboard and our touchpad interface. One of these over here was the hard drive connector. Actually, a lot of open space on this. This was our processor, and these are the blanks, the blank BGA and what I think is memory. We'll look a little closer in a minute. And then we've got memory down here. So let's hop right in to microscope view. By the way, out there in comment land, what do you like about Mark Void's warranty? What don't you like about Mark Void's warranty? What would you like to see more of? What would you like to see less of? What would get you to subscribe? What would get your mother to subscribe? Your sister, your brother, your father, your brother's father, your father's sister, your mom, your aunt? I don't know. But let me know. All right. Looks like our camera's a tiny bit rotated from mine. Let's try that. So over on the far right side of the keyboard, this is where we had our connections to the off-board connectors. They did a little via fence wall. It looks like that seems to be something of a standard practice along their entire board. What you're trying to do there is short one layer to the next. So on a multi-layer design, you're creating a spot of essentially zero impedance. So you can't launch, if signals come down and they start traveling, outside the board, the general idea is that they hit that fence and electrically it looks like a wall. So, you see vias here and they're placed, I'd have to pull out a ruler or something, but it looks like they're just about 0.1 inches on center. And then over here, some really, those are really thin traces. Probably unnecessarily thin. I don't know what those are, but those are at the lower manufacturing limits. Those are probably 3 mil traces. If you can make stuff a little bigger, make it a little bigger, because you do get manufacturing variability from time to time. Other thing that I'm seeing so far, and it might change, but I'm seeing all through-hole vias. HDI technology is expensive, and it's uncertain. So if you can do all plated through-hole, the old school stuff, your board's going to be more reliable. So we're seeing some missing parts. I guess they realized they didn't need them, so they're saving a buck. And that's pretty common. You put stuff in just in case, and then you take a look and see if you need it or not. A lot of differential pairs. Looks like they do some zigzagging all to get around this via for the part they don't need. Let me see if I can adjust the focus ever so slightly. How's that, Internet? Is that better? But yeah, so there's a via that's kind of far away from this pad. You do want the vias to have separation enough that you can have a solder dam. You don't want the case that that there's any chance that solder can wick from the pad into the via. That is a bad practice, bad juju. So they moved it off to the side. Well, moving it off to the side is good, except where were we here? Sorry. So they moved it off to the side, except they moved it way off to the side. If they moved it a little bit closer, or it looks like they could eliminate this entirely, you wouldn't have so much zigzagging in the traces. Now, does zigzagging in the traces matter? No, it doesn't. I'm just saying routing would have been easier. That's all I'm saying. So it looks like they did make some mistakes. So whenever you have a differential pair, or really any signal trace that transition layers, so like here we do, you want to have a return path, a ground return on each of those. But if you look, there's not even a ground port around here. So when the energy comes around here and it goes down into the board and it hits another layer, it's going to get noisy. There's really no way around it. There's no way for a return signal to find its way vertically without ground return vias. So here and here, it's possible that those are ground returns. It's maybe, I don't know. But you start looking around and you don't see that everywhere, and they have plenty of room for it. Sorry. So that's something that you do want to see. You do want to see ground return vias. I'm sorry, not ground turn, but just return vias. A space for the energy to come back on the other direction. All right, so we're continuing to look around. We're still stuck over here on the right side of the board, seeing if there's anything interesting. Not much. It's pretty standard layout stuff. They soldered the parts even if they didn't put them on. That's what these little balls are. They're non-placed items. This is I don't know if I'm seeing what I'm seeing. Yeah, this is interesting. So there's a pad here for some part, but that's a weird footprint, just a big rectangle. I don't know what you would put on there. Maybe a test point? Test point's the only thing I can think of that would make sense for that connection. All right, so we're getting over here, and we are now in still over kind of on the right side. We're over in the part that would be covered by the Wi-Fi. So this stuff would all be covered by it. And we're seeing some good layout practices. You've got a pour. You want to have a low impedance return, so you use multiple vias to tie one copper layer to the next. That's good stuff. I'm guessing these little guys are the decoupling capacitors. I always tend to move those things as close to the IC as I can without violating courtyard minimums. It's not going to make a difference. This little guy being, another millimeter out, does it matter? It doesn't matter, but it's just something I like to do. So we've got a transistor of some sort. One thing you do like to see, or always like to see, are teardrops, and that's what we see here. The reason being let's zoom in and I'll show you. So the reason is you can't always get those holes to go where you want them to go. Sometimes things are misregistered, misaligned. Sometimes the drills drift. So if it drifts in the direction of the trace, you can actually destroy that connection. So I never like to see that. So whenever you do have a via, it's always, especially on a very small trace, it's always a good idea to teardrop it or keyhole it or something. Or like here, I might even just move the via off to the side a little bit, because right now it's got two directions it can drift and destroy the trace. Well, it can't because it's teardropped, but I'm just saying if you didn't do that. But whereas if you move it off to the left, then there's only one direction that it can do that. All right, let's zoom back out here. I tell you, Mark has a nice microscope. Mark needs a fancier microscope. We need viewers. So how's it going out there in Watcherland? You guys have any questions, comments, concerns? All right, we're moving around. I don't want to keep you guys waiting too long. Let's get up into the IC. So just a bunch of the same stuff, nothing too exciting. All right, so here is our CPU. It's shiny and it's covered in schmutz. And I think I scratched it with the chisel. Sorry, CPU. But look at this tiny, tiny stuff. This is how these things work. So you take your IC die, and then you have all of these traces running out so that you can make enough connections on this. So on the bottom of this thing, you're going to see tons and tons and tons, absolutely tons of connections. And that's what all of these traces are doing on this tiny piece of glass. I don't know if I can show you part of that. We're going to find out. The answer is no. No, I cannot. But you can you can see some other interesting stuff, like you can see the fiberglass weave here. I mean, that's not tight glass. You would almost, I would expect to see flat glass in there. See if I can get under another layer. I think the answer is no. We're getting there, though. There you can kind of see the land pad a little bit better. I think I needed a smaller chisel today. So all those connections are connecting out to these little BGA arrays, just in an infinite number of things. And routing those things is a pain in the neck, let me tell you. So on the bottom side of that is a land pad that looks a lot like this, connections everywhere. And you can't always run those traces out the ways that you want to, like over here. You can see them running them out and running them around and getting the connections out. But when you get to this really high population stuff, really all you can do is just run it down to another layer. That's why you see these vias poking out. And you never want to put a via in pad because the solder will wick out of the spot and you'll never get into it. So anyhow, we're going to keep moving around. Nothing too interesting. This part of the board is highly populated. There's a ton of ICs and whatnot around here. You want to always, when you can, use multiple vias to connect your copper pores so that you have a low impedance path for the current to figure out which way to take. And then whenever you have a signal via, it's always a good idea to do a return via. And I'm not seeing a whole lot of those. So when you follow around these traces, these long ones are all signal traces. Oh, there's a sticker. I mean, and they're going for a long, long, long time. These things you need to worry about. I mean, we're looking at, you probably can't tell on screen, but we're looking at, 4 inches or so. So their paths are significant. And whenever these things terminate, like way over here, there's no real path for the signals to then go vertically. They might have a horizontal path routed under here. I can't really tell. But vertically, there's nothing for these things to do. So at that point, it's going to radiate out of your board. All right, let's take a look at the bottom side, and then we're going to move on to some other ICs. So here we're at the bottom side of the board. Looks like we've got a USB-C sitting there. How does that guy connect? Okay, I might salvage him later. But we've got USB-C, other ICs sitting around here. And some of these things require a lot of support circuitry, a lot of resistors and capacitors. So you can see that they've stacked these things, as close as they can. The silk screens are marking courtyards, areas that you want to give the pick and place machine so that, when they're placing the components as fast as they do, they don't collide with other ICs. And then it also gives you room to do a little bit of rework if you need to. If something fails or you have the wrong capacitor or whatever, you can get in and resolder these things, or skilled technicians can. Not mark with the chisel. So it looks like they used nominal or even most land protrusion layout. There's plenty of room around these things. A lot of vias. I mean, this is pretty much overkill for via stitching. What's on the other side of this? Looks like they might be using them for heat dissipation underneath some power ICs on the other side. But that's really kind of overkill. TI did a study, and there's an application note. But if you look at, what is it called? Thermal pad. If you look up like Texas Instruments, thermal and vias, I'm sure you'll find it. But you're going to find that they say, it's kind of a exponential decay. So after you get to about 9, it just doesn't, the return on investment isn't significant enough to worry about it. IPC, I always forget this one. Is it 7093? If Elliot, if you're still out there, maybe you can help me out with that. But it talks about how to make thermal pads for ICs. Best practices. Like this is not a best practice, because once you start putting solder on this, see how it's those vias that are tied right into the holes and there's no blocking? Solder's going to go into those. Gases are going to come out. You're going to get lousy pad connection. So anyways, let's see some other ICs. That was fun. What should we do next? Keyboard is kind of interesting. We don't have to look at it closely. But you've got this piece of stainless that might have been photolithography etched. I'm not really sure. And then on the other side, you've got, there we go. You've got the keyboard matrix grid. So all these little ICs going around making all these tiny connections. There's this thing called in-key rollover. At some point, as these things go over and they scan the rows, so the way a keyboard works, by the way, especially a big one, is that you inject a voltage, right? You would periodically go through each row and you would inject a voltage. You'd take it to logic high, and then you would scan each column and see which column is active. And it doesn't necessarily have to be an XY like it is here, but that's basically the way it works. That way you don't have to have one signal for every key. You just have to have one signal for each row and one signal for each column. Anyways, it goes through and it scans and it sees which ones are logic high. But since the rows are connected, if you have two keys that are next to each other and you press them down, the computer doesn't know which one you're talking about. If you have 3 keys, it doesn't know. You can start actually making it look like a 4th key is active that you never even touched. So the way around that is to use diodes in your design, diodes to isolate each one from the next, so you can't have current going backwards into the thing. But I don't see that here. So this keyboard, you would have been limited. You could have, if you touch too many keys at once or too many of the wrong keys at once, you could have gotten some errant keystrokes in there. So if you ever wonder why that happens, if you're going mash, mash, mash on the keyboard and things show up that you didn't expect, that's what's happening. All right. What else are we learning today? Let's get the tiny little logic, or not little logic board, but the tiny little input-output board next. That one shouldn't take too long. So here we've got USB audio, an FFC connector. Not too much here. You basically just have to run the signal lines along the length of the board over to where you need them and grab them there. So they just have a simple two-sided, I believe it's a two-sided board. We're going to find out here in a minute. Maybe. Which key do I need? There we go. I don't know what buttons I pressed. Mark smash. So nothing too exciting here. We have an FFC connector that does the input-output to the rest of the board. And then some connections. Again, we've got the same issue that we saw before. On these long runs, you want return vias. You always want return vias, because otherwise when this... Okay, so let me back up a little bit. Whenever a signal propagates along the lines, it is going to generate energy around the traces. And on an immediately adjacent layer of copper, the closest layer of copper to it, you want solid copper underneath it so that energy goes straight into that other copper, right? Differential pairs don't really couple to each other. They don't need to be next to each other except for noise admittance. So underneath here, we hopefully have solid copper, right? Until we get to whatever this IC is. On the traces that have to transition layers, and I forget which one of these was the one I was looking at a second ago. These things transition just fine. I don't remember. Okay, here we go. This is the one. So on these long traces, you do want copper underneath, but then once it goes vertical, you still need a continuous return path. That's why you want to put return vias right next to this stuff, and that's what I'm not seeing. We've got one that looks like it's might be doing its job, but what about this guy? Well, it's just going to radiate at that point. You don't want that. Bad engineering. Multiple copper ties throughout the copper pores would be better. It doesn't really matter. Depends on how fast these edge rates on these ICs are. So anyways, that's that board. This is the SD card reader board. So we've got one FFC connector that takes it off to the IC. Signals come in, drop down. Same issue with the copper read. Oh, wait, no, look. They did it. That's a return. That's a return right there. They did it, they did it, they did it. So we've got some sort of an SD controller IC that's probably doing buffering and controlling the SD card and all that. So it does all of that on board. So all you really have to send off board are the return, the data return, bring some power in, a 0-volt reference in, and then you're off to the races. So everything else here supports that one singular function. So probably we're looking at a 2-layer board. There isn't too much to it. I don't know if we can see in the edges there or not. I'm going to say no, I can't. Sorry, you're looking at my thumb, aren't you? See if I can get that in there for you. It's way out of focus because of the location. Let me see if I can back up here enough. So what we're looking at are the various layers of fiberglass that make up this panel. And 1, 2, 3, I don't know, there's 4 or 5. I still can't really tell. It's a little blurry on my end. But I'm not seeing any evidence of any copper mid layers there. So just a nice inexpensive board. The less layers of copper, the less expensive the board. All right, let's move on to our memory module. Boom, boom, boom. So our memory module has a couple of stickers on it that are in our way. We want to see stuff, memory module. We want to see stuff. All right, I think it's time for a viewer question. What has been the best part of Mark Voids of Warranty so far? Let me know, TV Land. Let me know. My voice is getting hoarse. I think I've been yelling too much. All right, so this is the VIA. Not the VIA, this is the memory. And the memory connects through a special edge connector to the rest of the board. There's a lot of connections, a lot of return paths. You know, here in this case, it's every other one. So as the signal goes, then you've got to return. Signal, return, signal, return, signal, return, signal, return. They're edge coupled, which isn't ideal, but, you know, what are you going to do? The basic idea is that you want frequent returns so that there is a path for the energy to take. All right, so here we've got, what is that? What are those white things? I don't know. I don't see any evidence of vias around this thing. So why would you have a capacitor going nowhere? On the back side, we've got, those are the vias that are just directly above it. I do not know. If you know, tell me, because I do not know. This is kind of an interesting trace. It looks like they had to increase the length, otherwise they could have just gone up there. You see a lot of these wanders, what they're trying to do is make sure that the signals that come in all, you know, after they travel, that they all reach their destination in the same time. It's not about distance, it's about time. Because the general idea is that you want, when the clock line strikes, you want all the data lines to be at the same logic level that they're supposed to be. So the way that you do that is through length matching. Now, length matching is the primitive way to do it. Really what you want to do is actually go for time matching, you know? So you have to know what the impedance of your trace is. It's going to be different if you're on the surface versus in the surface. We've got microstrip versus strip lines that we call them, because when you're on the surface, part of your impedance calculation includes the air space around you. Once you're in the board, really all you have to worry about is the impedance of the fiberglass. So time matching is what you're going for, not necessarily distance matching. So usually you don't have to worry about it. This stuff is fast, but it's not that fast. Brian says, It's hard to pick just one, the humor, the good information, and the hammers. I love my hammers, especially that little drilling hammer I was using today. I need to go get another one of those, just in case they stop making them. It's a good one. All right, so here we've got one of the memory modules, and you've got decoupling capacitors. So we've got decoupling capacitors placed relatively close, a little further enough away that if you needed to reflow this module, it wouldn't be a problem, but they're close enough. Tied right into a big fat ground pour, and then you've got the return path. So there's capacitors placed all over the place around here. Bigger ones likely have a tiny bit more capacitance than the smaller ones, but they've all got very low inductance because they're small package sizes. And the package size has a huge influence on the inductance. So nothing too much to see here. It's interesting stuff. Coming in off the thing, we've got just some inline resistors to keep ringing down and whatnot. And then they did a little copper name thing. That's cute. So big fat copper. Little bit of edge stitching via fencing, not too much. I probably would have done a little more just because I like doing it and it doesn't hurt anything. And then you've got a lot of tie-in down here. So I wonder what's going on over here. I don't know. Have to see a schematic to better understand. And then the backside. More memory. Looks like it's pretty much the same thing. Just a big fat memory board. I don't know if we're going to be able to see into the edges on this at all, but we'll give it a shot. All right, so I can't even make out any, barely make out some fiberglass layers. This is a much more consistent inner dielectric. That looks clean. So this is a much tighter fiberglass epoxy core that gives them better control over the impedance than the last board we saw. So this has higher edge rates, so it's a higher quality dielectric material. But I can't see into it at all. I can't tell you if there's inner layers at all. Sometimes you get a hint. You're always supposed to pull the copper back, 12, 15 mils from the edge. So this is so tight. I just can't. There you can see. So they used a flat glass. You can kind of make out 1-2 layers of fiberglass there. There's certainly more, but maybe they used a flat glass. I don't know. I'd need to talk to one of my board makers to know it. Josh says, I dig the humor, the information as you talk us through the design. It's nice to see the inside of hardware I don't have to explore on my own, as well as it to take your take and commentary as you go on. Hammers and chisels never hurt either. Don't they? Don't they? I hid that injury from you because I was ashamed. I had a boo-boo. All right, let's see what else we got. We're not done yet. Okay, so one of the buttons I pressed changed my thing. We are not done yet. We have a screen. All right. How do we get into Mr. Screen? Usually on a screen, there's something down here that lets you get into it. Oh, we're coming up on the hour. What do you think I can do, viewers, to get more viewers on Mark Voids a Warranty? How can we make it more popular? How can I get more YouTube street cred? Does it need to be sexy Mark Voids a Warranty? Just asking. Okay. I'm just going to hurt myself if I keep doing that. The chisel's too big. We're going to see if we can't get underneath this. it looks like there's a tiny little edge there. There we go. All right. So on those friction hinges, which are now loose, we've got some screws. Big fat ones. So that should let us remove these friction hinges, and then we might be able to get into our LED patterns here. Most of these monitors, just to make them so thin, they're edge lit. So there's a LED at the bottom or on the sides, just a big fat LED strip. And then they use plastic to, and some diffusion screens to spread the light out. And that all happens behind the screen. You never get to see that. And then the screen itself has all these little crystals that are captured between two polarizing plates. And there we go. And the screen then energizes those crystals, and they make different colors. We got lots of tape here. Lots of tiny screws. All right, we're running against the clock. You guys still with me? We got 4 minutes. What about the time of day of Mark voids a warranty? Is this a good time, a bad time? Should we do it at a different time? I don't know. Okay, so while I'm working through this, I do have other good news for you. We've got a design competition coming up in mid-March. We're going to give away over $500 in prizes. I don't know about you, but I'm excited. All right, this screen is not wanting to come off the bottom of that board. It might be glued in. I'm not sure. I don't see anything hardware-wise that's holding it in. But man, I tell you, I am putting a lot of force on that, and I'm not seeing any movement. Something is holding strong. Ha ha ha. I can hear glue giving way slowly. So really what we should be doing here, I believe, is heating it up. That glue does not want to let go. Okay. That was good glue. 3M, good work. Yeah, we really should have heated that up, but I don't want to keep you here that long. So what you have is an LCD, and on the LCD, there's 2 layers of polarizing filter that are cross-polarized. And in the middle, there's this liquid stuff, and it's a crystal. And when you put things between 2 polarizers, you get to see stuff. Let me see if I can demonstrate that at all. I might need to grab a light. So we're going to need a backlight. We need a backlight. We need a quick backlight quickly. 1 moment. What do I have? What do I have? Here we go. All right. Sorry to keep you waiting. So you put a crystal in between these 2 polarizing filters, And as you rotate it around, you can start seeing different colors and different shapes. This is probably not my best example I've ever come up with. Do I have anything else? Here's some plastic. Let's see what this does. Not much. But anyways, that's kind of the basic way that these things go. Let's see if we can... There we go. So this is our absolute minimum light situation. I can barely see colors in real life, and I don't see anything on the screen. So I'll have to come up with a better demo for you at some point. Anyhow, the way that they spread the light out is you put LEDs. You put LEDs at the bottom, and then you shine them up into a piece of plastic like this. The plastic has lots of little dots and deflections and schmutz on it, so it tends to bounce the light out. Hits a diffuser panel on the front, a reflective panel on the back, and then it hits these things, which are big fat multi-direction diffraction gratings, and they bounce light in all directions. And this is your reflection panel on the back. Anyhow, that was Mark Voids a Warranty. That is what it looks like when you try to oppress Mark. That's right. The man was trying to get me down. I did not let him. No! Don't let the man get you down. Join me next week for Mark Voids a Warranty. We'll be taking something else apart. I think it's a telescope. I'll have to go look. But whatever it is, it's going to be fun. I really appreciate you spending your lunchtime with me here. This is sponsored by Royal Circuits. I'm Mark, and it's been a pleasure having all of you here. So Elliot, Josh, Jason, Brian, and anybody else that I might be missing, thank you for spending time with me. I had a blast. I hope you did too. Make sure that you share this. Encourage your friends to subscribe to Advanced Assembly's YouTube channel. We always have fun here, or at least we try to. And every now